Good afternoon, everybody. It is a real pleasure to see so many people here for this week's joint colloquium. And it is an even greater privilege and honor to introduce Alice Deason from Durham University. Alice is a renowned expert in galactic archaeology, the accretion history of the Milky Way, the galactic halo, galaxy formation and evolution, galactic dynamics, and the entire satellite accretion history of the Milky Way. Alice operates on the interface between observations, theory, and simulations, basically picking all the interesting topics that we're all excited to hear about. And that journey started with obtaining her PhD from Cambridge in 2012. We met there a couple of years before that, after which Alice took up a Hubble Fellowship at UC Santa Cruz, moving on to a Porat Fellowship at Stanford, and since 2016 she is a Royal Society University Research Fellow at Durham University on a tenured position where she is now building her research group. And today she's going to talk to us about the galactic halo renaissance. So please give her a very warm welcome.
Thanks a lot, Deirdre. Can you all hear me? Is this working? Yeah? Okay. So it's a pleasure to be here, and I realize this is actually the first time I've ever been in Heidelberg, which in itself is a travesty given what I work on. But I finally got here, and it's a very beautiful place to be, so thanks a lot for the invite. Okay, so today I'm talking all about the galactic halo, which is a subject very close to my heart. And it's mainly going to be based around what's happened in this field in the last couple of years, particularly since the Gaia data releases. And I call this the galactic halo renaissance, because I really think we've made so much progress in the last couple of years, and it's about moving forward from that work. So I want to start off with just to kind of introduce what the galactic halo is, what I'll be talking about, and I'm showing this with a simulation. So you can see on the left, this is an image that you're probably all familiar with, a dark matter halo of a Milky Way mass scale, and then slightly zoomed in to what the stars look like in this halo. So you can see that density redder is more dense regions. Most of the stars are in the very central regions of the galaxy. But you can also see there's this kind of diffuse envelope of stars, which we call the stellar halo, and then these kind of little knots of stars, which are the dwarf galaxies. So the populations that I study are basically things that are far out from the central parts. So where all the baryons are, this kind of 1% of stars are in the stellar halo, and that's where most of my work is based around. Now this is a simulation, okay? And the prevailing theory from these is that you get dwarf galaxies over time accreted by the Milky Way, and some of those lucky ones survive, and then some of them get destroyed. And we think at least a significant amount of these stars in the halo are just the destroyed remnants of dwarf galaxies over the assembly history of the Milky Way and similar galaxies. Now this is a nice picture because this isn't reality. What does reality look like? So this is probably the most famous image in the field, or has been for some time. This is the field of streams. This is SDSS data. So I'm showing an updated version. It's the original field of streams made by my esteemed colleague, Vasily Belukharov. And what this essentially shows, this is using just photometric data. Stars are basically colored according to distance. So as well as spatial information, the color information tells you about distance. And what this image kind of reveals is all the substructure and structures that we have in the Milky Way halo. And most prominently, of course, the Sagittarius stream, which kind of pops out very, very well on this image. So we know from observations that the halo is littered with streams and substructures, and we get to see both the surviving and the perished dwarf galaxies in the halo. So you could ask, this is 1% of the stellar mass in the stellar halo. The dwarf galaxies, these tiny little things. Why would you want to study this component of a galaxy? Okay, and I think this talk is going to be in 3 parts, and hopefully I'll get to the end. Basically focus on what I think are the 3 key things that we can learn from the galactic halo. So one is dark matter. Okay, these populations, these dwarf galaxies, these stars, they're in the regime where the dark matter dominates. So these stars, streams, globular clusters, satellites, they can extend out to the virial radius of the galaxy. And that means we can probe the mass distribution. So, we've known that most of the mass in a galaxy like our own is not visible, it's dark. And this is a way we can probe that. Also, these lowest mass dwarfs, they're really at the boundary of what we call a dwarf galaxy. Some of them are so low mass, we're near the edge of where subhalos, that there are subhalos that don't have any stars at all, okay? And so that's really a probe of the nature of dark matter. The second thing, which I've spent a lot of time working on, is galactic archaeology. The idea that in our Milky Way, we can actually probe galaxy formation star by star, which is what makes it such an attractive field. And then it's almost like these populations have a memory of the galaxy's assembly history, and we can try to piece that together. And finally, something I hopefully will touch on toward the end of the talk is the field of near-field cosmology. The idea that probing stuff in the Milky Way today tells us something about the early stages of the universe, and in particular, for example, the population of dwarf galaxies can tell us something about the epoch of reionization. Okay, so I'm going to start with dark matter, and how we can use populations in the halo of the Milky Way to probe this. So the first question, which is kind of the first thing you can say, is how much mass is there, okay? For our Milky Way galaxy, how much mass is there? How is it distributed? Now this has almost become a kind of a parody, this question, what the mass of the Milky Way is, because there have been years of measurements and such big disparity in what those measurements are. So I like this plot. This is a compilation put together by Wenti and Wang. And I think it only covers the last decade, maybe even more recent than that. And it shows a range of measurements that have been taken. You can see some are very small error bars. They don't always overlap. And actually, there's probably uncertainty there by a factor of 4, okay? Which is a pretty embarrassing situation to be for your own galaxy. If you look at people study external galaxies, and they often quote masses to much better than this. So it's pretty terrible that we don't know the mass of our own galaxy that well. And it actually turns out to be a huge problem, because this is a degree of freedom in a lot of measurements we make. If we want to know what the orbit of a star is, we need to know the mass of the galaxy. If we want to compare it to a population of simulations, we need to know what the mass is, okay? And I think we have had a lot of excuse for why we've got such uncertainty. We have systematic errors that haven't been quantified very well. There's methods that haven't really been tested, noisy data, missing data, and I think there's a lot of get out of jail cards for why we're in this situation. But now we have Gaia, so now we have no excuse anymore for not knowing this quantity of our galaxy. Okay, Gaia's going to solve everything, so it's going to have to solve this. Okay, and I'm giving a teaser because this is a measurement that I'm going to talk about, where now we think we've pinned down the mass to more about like 20% rather than this kind of big factor. Okay, so what I want to talk about first is a paper that my student, who's now in his 3rd year, I believe, Tom Callingham, an incredibly talented student that I have, and this is a paper that came out earlier this year. So the idea of this work was to use dynamics of satellite galaxies to measure the mass of the galaxy. It's something that's been done before, but what Tom did that was different is first that he used the latest Gaia observations or HST data, so we have 60 phase space for all the classical satellites. And then he compared to satellite dynamics in a simulation, in particular the Eagle simulations, okay? And actually, it's quite a simple concept of how we go between these two things. So first you have to appreciate that what we observe are instantaneous quantities. We observe positions and velocities, and that's what's happening now. In order to go to conserved quantities like energy and angular momentum, a space that we often like in dynamics, we need to know what the mass is, okay, to go between these two quantities. So what Tom did in Eagle is he took all the systems which were in the very broad mass range of a Milky Way, and he just plotted the energy and angular momentum distribution of satellite galaxies, okay? And these are stacked together, so they're scaled according to mass so that you can stack all these systems together. And that's in the simulations, okay? So to compare to observations, so let's take an observation of the LMC. Okay, we know its position, its velocity, thanks to these new proper motion data. And if we want to put it on this plot, we have to assume a mass. So if we assume a mass of 1 times 10 to the 12, the LMC goes there. If we assume different masses, it goes on different places on this diagram. Okay? So the idea is if we make the assumption that this distribution in the simulations is representative, then we can join these points together and create a PDF of what the observed parameters of the LMC tell us about the mass of the galaxy. So you can just follow this along. Basically, the denser regions are the higher probability regions, and then we can create this track for the LMC. Now, the idea is that we have more than just the LMC. We have all the classical satellites, so we can actually combine all these measurements together to get the combined PDF. And that's what Tom did in his paper, so all the individual satellites, and then this is the combined answer. So at this point, you could ask, okay, but why is this a better measurement? One thing that was done in this paper, and I would urge you to read it for more detail, is that this was thoroughly tested on different suites of simulations. So we did exactly the same thing on the systems in Eagle to make sure we got the right answer back and understood the error distributions. We also did it to a different suite of simulations, the Auriga suite, which are a different code, and again, calibrated the errors in that way. So we kind of trust this almost like 20% error, which I'm not biased at all, but I think is the best measurement of the Milky Way mass to date. Right, so that's one way to do it. And again, this was post-Gaia, so we had this brilliant data in order to do this. And I now want to talk about another way to get the mass of the Milky Way, a completely independent method. Again, something that we can only do thanks to Gaia. So this is using the galactic escape velocity. So this is a very, very different measurement to measure the dynamics of satellite galaxies. This is looking at the fastest stars in our solar neighborhood. And why do we want to use those stars? So basically, these stars are the ones that, they're moving the fastest, and they're the ones that potentially, because they're moving so fast, can go all the way out to the edge of our galaxy. And the nice thing about the escape velocity is that it's a local measurement. It's within the solar neighborhood, but it can tell you about the total mass distribution, which is not something you can do, for example, with circular velocity measurements on its own. So this kind of thing has been done for quite a while. It dates back to Leonard and Tremaine, who came up with this approximation that you can model high-velocity stars, assuming they're all bound, just by modeling the tail of the velocity distribution. Okay, and they had this very simple formula that just relates the distribution just depends on escape velocity, which is the thing we want to get out, and the shape of the high velocity tail. Now it's this shape, which we call K in this here, which is like the big unknown in this type of analysis. So the problem is, if you look at this plot here, this is the shape parameter, this is escape velocity, there's a very big degeneracy between the two, okay? So what has been done previously, there's some really great work done by the RAVE teams when they only had line of sight velocity doing this, was basically they constrained the shape from simulations. They looked at simulations, say what should the shape be, there was a range of values, and that was used as a prior in their analysis. But the problem with that approach is there's a wide range of these shapes in the simulations. Every halo is different. The shapes of velocity distributions change. So there's a wide range of values. So the thing that we did in our work to put this a step further is to say that, well, I think we know a lot more about our galaxy, to not just have to do a prior from simulations, actually use the observations to guide us in order to do this. So that's what we did, and I think the first thing is to explain how the shape of this velocity distribution depends on some observational things. So what I'm showing here is complete toy models, okay? So just concentrate on this side for now, and this is exactly the same potential, total mass, and all I'm changing is the velocity anisotropy of the stars, so whether their orbits are more radial or more tangential. And essentially, more radial orbits give you this more extended tail to high velocities. All of these three have the same escape velocity, they just have different shapes. And you can actually see that this shape kind of directly scales with the velocity anisotropy very nicely in these models. It also scales with the density profile of the tracer stars too, which is shown by different lines here. So that's kind of, this is a toy model, but it's a very simple relation between these things. But the thing is, we know these for the Milky Way, okay, which this isn't an unknown. I'll come back to how radial the velocity anisotropy of the Milky Way is, but we've actually known for some years before Gaia that it's very strongly, the anisotropy is very radial, okay? So we know this. We also have a pretty good handle on what the density profile looks like in this distance regime. So we can do better than just assuming a wide range of k values and do a prior. We can be a bit more informative. And you could ask then, okay, this is a complete toy model. How do you know this works in reality? So we actually tested this on simulations. So these are the Auriga hydro simulations of Milky Way type galaxies. And you can see that this is the shape against anisotropy. And there's more scatter. But interestingly, this line is basically the toy model. And it actually was surprising at the time that we did this that actually has any agreement at all with this very, very simple analytical model. So I've highlighted here something I'm going to come back to soon, this kind of regime where highly radial sausage halos, which I'll come back to why I call it that, but this is kind of the regime we're in for the Milky Way, this very highly radial velocity anisotropy. Okay, so when we applied this to DR2, we basically just took the high velocity tails. We only used DR2 stars locally that had 60 phase space, so we limited within about 3 kiloparsecs to really make sure our parallax was informative, for example. And then we basically applied this technique to find the escape velocity using the Leonard and Tremaine approximation. And again, so the first thing to notice is this is the shape, this is escape velocity, and this is the degeneracy that we always get. And then what we do is that we add on the prior. So the prior based on what we think the anisotropy of the halo stars is, observationally motivated, puts us in this regime. The kind of priors that used to be used from simulations give you basically a higher escape velocity. And then of course, then we want to go from escape velocity to total mass. To do this, you have to say, well, where do these stars escape to? And again, the paper has more details. We essentially said, looked at simulations to what this probably is, to about 2 R200. We also combined this escape velocity with circular velocity constraints. So if you look in this is concentration mass. Our escape velocity curve is the gray region, and then the blue is circular velocity, and then combined is in the red. And what we get out of this, basically with this new prior, is a mass of 1, suspiciously close to 1, I would say. 1.00 is kind of worrying when you get that out, because it looks really contrived. But I promise there was nothing contrived in this. It really was, that was the answer. The error bars are larger than the Callinan method. But that was the mass we got, which was actually using exactly the same data, significantly lower than what had previously been found. So that's not the end, and for this estimate, that's not the end of the story, because this is, although I think we've made steps understanding the shape of the total velocity distribution, there's still a lot of things we need to tidy up. And in particular, we did a follow-up paper, so Rob Grand led this, looking in more detail at the simulations of how we actually make this escape velocity measurement. And we found that typically we actually underestimate by about 7%, which doesn't sound like a lot, but when that goes to a mass estimate, that's about 20%. And we think this is because if you built the halo stars, if they come in very early, don't reach out as far as today's 2 R200, okay, because the halo grows with time. Unfortunately, this is a general statement, and in the case of the Milky Way, we have to do a lot better to understand this exact point. But if we make the correction just assuming the Auriga halos are representative, then we get a mass at 1.3. So in reality, the answer probably lies somewhere in between. And funnily enough, the previous measurement with Tom that we did with satellite dynamics does actually lie exactly in between these measurements. So I think we've got some sort of convergence on where the mass should be. Okay, so the very last thing I want to say about mass of the Milky Way is not just talking about the total mass, because we want to do a lot more than that, is now also look at what the mass distribution looks like. So this was a paper that actually appeared in the archive a few weeks ago now, I think. This was led by a postdoc, Maris Khatoon, who's now at Leiden, who was at Durham. And the idea of this project was essentially to look at all the different mass measurements we have, basically circular velocity measurements of the inner galaxy, Tom's measurement of the total mass, and then fit like a basically a whole profile to these data points. The difference was that Marius looked at the adiabatic response of a dark matter halo to baryonic component, which is often not adjusted for when people do these models. And the idea was that, this is he did the fit both with and without contraction to see what the different results were. So it turns out, unsurprisingly, that halo contraction doesn't matter. How the dark matter halo responds to the fact that you have these baryons right in the center. It pulls the mass in and changes how you model the mass distribution. So if you look at, essentially, if you look at a contracted halo, gives you a higher mass and a lower concentration. And it's kind of this degeneracy between the two. And again, the mass here is almost exactly 0.99. And in fact, the concentration he gets out, if he assumes contraction, is in perfect agreement with what is predicted for lambda CDM at these mass scales. So again, that's like now going towards the mass profile. At this point, the data is not good enough for us to actually say if an uncontracted or a contracted is a better fit, which is something that we should be able to do in the future with further data releases. Okay. So I think my personal optimism for this field of looking at the total mass of the galaxy and measuring its mass distribution, I think is that we're really starting to converge on an answer that people tend to agree with. People, I guess, can correct me if they think I'm wrong at the end. But I think we're in a much better position than we were before Gaia came out. Okay, so the second thing I want to talk about, so talk about the mass distribution, dark matter, mass that we can measure. So now something that I spent a lot of my PhD work on is galactic archaeology, the idea that we can use the populations in the halo to tell us about the assembly history of the galaxy. So, of course, when we talk about dark matter halos, the famous NFW profile, dark matter halos are, they're approximately universal. You can scale them at different masses, and they kind of have the same sort of distribution. Stellar halo formation is a much more stochastic process. Okay, you have much lumpier accretion. The stellar mass-halo mass relation at the dwarf scales is quite unknown, but it's very different. Depend on different models. And also the stars are deeply embedded in the dark halo, so they get stripped very differently to the dark matter. And all that results into a very big variety of stellar halo profiles. So here's a nice example. So these are the 6 Aquarius stellar halos that Andrew Cooper did almost 10 years ago now. And these all are very similar halo masses. The dark matter distributions all look very similar, but the stars all look very different. Okay, and that's just basically saying that even just looking at them, their assembly histories show that they look different just in the spatial distribution. So just to kind of do the first order thing, which is basically count stars as a function of distance, if we do this, and that's been done for a number of years, I should say, then you get quite an interesting feature in the Milky Way. So, but this dates back to one of the first papers I did in my PhD, and we found using SDSS data that if you go beyond a radius of 20, 25 kiloparsecs in the galaxy, the density profile drops off much faster beyond that point. So it's called a break. Brownie says I've also done a lot of work on this. And the idea is that you can't just fit the data. So the data in this plot this is number of stars, function of radius. Black is the data. If you try to fit a single power law, it doesn't agree. A way to do this is to actually fit a break, what we call a break in the density profile. Now you could say, well, is this a generic feature of stellar halos across lots of different galaxies? And the answer is no. You only need to look at M31, our nearest neighbor, where people have mapped out the profile of halo stars, and that actually follows a single power law quite nicely of a very large radial range. Okay, so this is not a feature that's generic. So back in now 2013, which seems a long time ago, we tried to understand why the Milky Way has this distribution of stars. Why does it have this break in the density profile? And we actually attributed this break to the buildup of stars at apocenter. The apocenter is the furthest point of a star's orbit, and the idea is if the stars all came in from one dwarf galaxy, and they all have quite similar apocenters, and the break is essentially the edge of where that massive accretion event at that apocenter. I'll show in a bit why we thought that. And then we kind of made this, we didn't have a lot of evidence, but what we thought was going on is that maybe this means there was a relatively early massive accretion event that dominated the inner parts of the halo, and then this break is basically where, beyond that, it's not dominating anymore. And I should say that when we did this back in 2013, I'd say it's fair to say no one really believed this, including some of my co-authors, so I won't name who it was, who didn't believe this. But I don't think there was much traction that this is actually the reality of what's going on in the Milky Way. So to understand why we see this break radius, kind of nice to show an example. So this is looking at individual accretion events in Bullock and Johnson suite. So this is just a numerical n-body suite of just dwarfs being destroyed in a potential. So if you look at the kind of what we often see is this kind of shape. This is stars all destroyed from one dwarf, and you can see this break in the density profile just coincides of where these stars are at epicenter, where their radial velocity is essentially, the dispersion is close to zero. So of course then, that was the kind of prediction that this massive accretion event happened in the Milky Way. But then, then Gaia came along, and then we couldn't just make kind of broad assumptions based on the limited data we had. Then we could look at this in a lot more detail. And what came out actually before the second Gaia data release, so Gaia DR1, Vasily and collaborators, particularly Sergei Kopsov, I should give a lot of credit for this, cross-matched DR1 with SDSS data to get some very good proper motion measurements. And so Vasily in this paper looked at nearby stars in circular motion and radial motion, and he found, if you look at the kind of the halo component, it's very elongated, so he came up with this fabulous name of a sausage to explain this shape, and then of course this is the disk distribution. So in this paper, it was inferred that about 2/3 of the local stellar halo is in fact in this sausage component. The stars, these tend to be actually more relatively metal-rich for stellar halo, so 1/10 solar. But the main thing is extreme radial anisotropy. And this was the conclusion from this, a head-on collision with a massive dwarf. Now, this wasn't the only more recent evidence we had for this event. Of course, there was an independent discovery in Gaia DR2, led by Amina Helmi, and it was termed Gaia Enceladus. It's basically talking about the same thing. And again, this kind of very radially anisotropic component was seen in Gaia. Also, there was independent evidence from the globular clusters. So in particular, Myong, also with Vasily and Wynne, actually showed that several of the globular clusters, looking at their energy and action components, aligned with this sausage event, so having very radial action, for example. And then also some work that Deirdre did. Actually, this predates Gaia. Originally, it's 2019, but this came before. This wasn't using Gaia data, so this is completely independent. They found basically the Gaia sausage component, and then also maybe a second massive accretion event at early times. So again, I think there's a wealth of evidence now. There's been at least one massive accretion event which dominates the inner halo since in the last couple of years. So we went back. One thing that we did when after this evidence for the Gaia sausage, Gaia Enceladus, which was one of the most exciting things I think to come out of Gaia. We went back to this idea that this break radius is the buildup of stars at epicenter, because it was an inference, if you like, for comparing simulations to data. But we went back and actually looked at the orbits of these stars, see if this was actually the case. So here, this is looking at local main sequence stars, and also looking at distant BHB stars. If we look at the relatively metal-rich populations, this is apocenter versus pericenter, we did actually see that the stars tend to have apocenters, which actually coincides with the break radius, which was kind of what we predicted, and it was kind of nice to see it actually come out from the Gaia data. Now, you can also do this with globular clusters. This is also something that Myung did in his paper, looking at these globular clusters that are probably associated with this event. And again, their epicenter kind of coincides with where we've seen this break in the stellar halo density profile. Okay, so I've talked about, we think that there's been this massive accretion event, but how do we know this was ancient? Okay, that's kind of not, it's an ancient, massive, but you want to quantify both these things, how ancient, how massive. And one thing you can do is compare with simulations. So there's been some great work, so Azi Fatahi, Ted Makarov have done this sort of stuff. You can also do the accretion of globular clusters. The eMosaics team have done quite a lot with this. Even if you just look at the ages of the stars, if you look, just from their color magnitude diagrams, they agree with like a 10 to 13 gig-year population. And then more recently, which I'll come to now, we actually looked at the idea that what the total stellar halo mass is, and how we can reconcile that with the fact that the Milky Way stellar halo is supposedly, or until recently, people have thought relatively metal poor, so an average about -1.5. How do we reconcile that with, a potentially up to 10 to the 9 accretion event? Okay, so an important question from this is, where did the mass go? Okay, you can talk about accretion events that happened, but if these massive accretion events happened, what happened to the debris from these events? Okay, we know there's some there, but how does that relate to the mass constraints? So data and simulations suggest Gaia sausage is maybe a 10 to 9 event. Okay, if that's true, or maybe there were two events that were less massive than this, but where did all that mass go in the halo? And particularly if you look in the literature, that mass estimates for the stellar halo of the Milky Way are more like half of that, maybe 4 to 7 times 10 to the 8. There's a bit of a disparity there. If we think these massive accretion events have happened, why is the stellar halo mass not that massive? And in particular, this is a theoretical piece of work I did looking at how the total mass in the halo relates to the typical progenitor. So if your typical progenitor is 10 to the 9, the total mass is about 10 to the 9, because it's really just dominated by this one accretion event. Okay. So one thing that we wanted to do we wanted to use Gaia data to tell us what the stellar halo mass is. Okay, and that was what to kind of tie up this loose end of why the stellar halo mass is low if we've had these massive accretion events. So to do this, we used pure DR2 data, and we essentially looked at red giant branch stars. So the idea was to just look at very red stars. You can see this selection here, and just use a parallax cut just to get rid of all these close-by dwarfs. But that means you're basically left with disk giants and halo giants. Okay, and the trick that we use to do this, essentially, because what we have from Gaia is proper motion. So there's no radial velocity, just proper motion. And the point is that even though the disk and the halo, they have different dynamics, but the real distinguisher in proper motion space is the fact they're at different distances. So the halo stars are much further away, so that means the proper motions are typically lower, much lower than the disk stars. So we wanted to use this fact to separate them in proper motion space. So the idea was that we modeled everything with a disk and a halo component. We just assumed 2D Gaussians to measure the proper motion distribution. The idea is this is just the model and some data. So as you go to redder colors, your giants become more distant, and you get narrower and narrower proper motion distributions. So we basically used this to separate them out. And that basically allowed us to count the number of red giant branch stars, just using Gaia data in different, so we did this at different magnitude bins, different color bins, and then different regions on the sky. Now we want to relate that to the total luminosity or total stellar mass. So that means we need to do a stellar population correction, so relate number of red giant branch stars to luminosity, and that depends on what color you're looking at, for example. We also need a volume correction because we're looking at different regions of the sky, different magnitude bins. So we need a volume correction. And in this, and there's a lot more details in the paper, we have to make some assumptions. So we assumed a metallistic distribution function and a density profile, and we actually look into what the systematic influences of these assumptions are in the paper. But the long and short of it is if we put all that together, we slice up the Gaia data into all these different bins, measure the luminosity, we get an overall stellar mass out, assuming a Krupa IMF of almost 1.5 times 10 to the 9, which is significantly higher than previous measurements. Now, interestingly, whenever you get an answer that is different to everyone else, you also get a lot of, obviously, why is that? And you have to look into that. One thing that was particularly pleasing when we did this at almost the same time, Ted McGrath and Joe Bovey actually had an independent estimate of the stellar halo mass, and they got 1.3 times 10 to the 9. Again, using the new Gaia data to do it in a very different way. So it's actually quite encouraging that we're getting a more reasonable answer. Okay, so as well as the new measurement of the stellar halo mass, very recently, so Charlie Conroy had a paper arguing that the stellar halo metallicity should also be revised. So not only should the stellar mass be higher, the metallicity should be higher too. And actually now, in this context, the Milky Way looks a lot more normal on the stellar mass-halo mass relation. So we probably need more measurement to see if this really is the case, the metallicity is higher, but we seem to be going in this direction where it used to be considered something like down here. But regardless of the fact that maybe the metallicity is higher, we think the stellar mass is higher, if we compare with other galaxies or even simulations, so if you look at the fraction of stellar mass in the halo versus the galaxy mass, so obviously fractions are very low, you can see, so this is the Milky Way, showing simulations of the grey boxes, and then some data from ghosts and dragonflies also shown. The Milky Way is still kind of low, even given the revised mass estimate. And I think when we looked into simulations, the one possible reason that can be is just simply that it's an early forming halo. If the big accretion events happened early, then that does give you a smaller fraction of stars in your halo. And that's probably the only way that we can reconcile these things. Okay, so I think if I have time, the last topic I want to touch on, so I've talked about the dark matter mass, galactic archaeology, and now something that probably is, I'm moving into a bit more, near-field cosmology, just based on the institute I'm at, which is a cosmology institute, how we can use stars in the Milky Way or populations in the Milky Way to tell us about cosmology. So one of the big questions that has kind of, on the small scales, has been, or used to be, a problem for our model of lambda CDM is what's, I'm sure you're all heard of, the missing satellites problem. The idea that if you look in cold dark matter simulation, you have all these substructures, but if we look at observations, even with recent discoveries, we're of order 50. So this has been, this has been talked about for many, many years, this disparity between these two pictures. Okay, and again, we've of course made a lot of discoveries, so going from photographic surveys to digital surveys, of course, has made a massive improvement. I'm sure we'll find many more in the era of LSST, but there's still this kind of uncomfortable difference between dark matter only and the observed universe. Now, of course, this was, if I talk to the director of my institute, Carlos, he would say this was solved many years ago and doesn't know why people are still talking about it. So there's, for example, a paper by James Bullock who showed that one way that you can get rid of all this substructure at low mass scales is just reionization, the fact that the universe reionizes. Basically, that event suppresses stars forming in the really low mass dwarfs, because basically they just get blown out and they can't keep hold on to their gas. And this kind of just using a simple model can account for that. That plus of course, the idea that we have selection effects when we make observations. We don't see everything when we look at the dwarf galaxies, and this is particularly true at the faint end. So of course, so Sergei Kopsov had a paper about this, again, almost a decade ago now, showing how these corrections actually make us much better in line with the theory. So you could say missing satellites, maybe that's not a problem anymore. But what this does mean, if you look at just this plot, which is now almost 20 years old, is that reionization affects the luminosity function of the dwarf galaxies. Okay, so we can use it to solve or partially solve the missing satellites problem, but it also means there's information in our observed distribution of satellites about reionization. Okay, because different models will give you different things. Now, the one point I want to make from this slide is this is the cumulative luminosity function. Okay, so in circular velocity, it's the same thing. And this is how it's often plotted. Okay, the cumulative distribution, so it kind of looks like this. And one thing that we did, which I think actually shows more information, is not to plot the cumulative distribution, it's actually to show the differential distribution. So this was a paper that, this was in a paper again, I think this is maybe the only thing I'm going to talk about that isn't using Gaia data. But this was Saunak Bose, who's a postdoc now at Harvard. He was a PhD student at Durham. And he looked at dark matter-only simulations, high resolution, plus a semi-analytical model to model your galaxy formation. And again, he focused on just looking at the luminosity function of dwarf galaxies. And this is a cartoon he came up with to try and explain what happens when you change the reionization parameters. So again, this is differential distribution rather than the cumulative. And what you see, if you look at some standard model, you get these two peaks in the luminosity function, a population that are formed before reionization and a population that are formed afterwards. And of course, if you change the epoch of reionization, you make it earlier, you have less dwarfs formed before reionization, or you make it later, you get more. You can also change the mass scale at which reionization has an effect. So that moves. So basically, if you affect more massive halos, then the change affects the more massive ones as well. Now, for this, the mass scale at which reionization matters, we have much better handle on because we know the luminosity function, for the bright galaxies in the Milky Way fairly well. So we can actually put constraints on what that should be. But at this faint end, which really affects how many ultra-faint dwarf galaxies we should observe, when reionization actually really matters. Okay. So what Saunak did, and it's kind of like giving it away in one slide, but what this is showing, so the data points here, this is the combined Milky Way M31 differential luminosity function. It's got a correction that Oliver Newton did, a PhD student as well at Durham, for survey selection biases. But this is what the data from the combined shows. So you can see this kind of characteristic. We had a lot of flack about this data point, that kind of everything gets thrown off, this is gone. But I think statistically, this actually, it looks like two populations. And this line, this like orange line, is actually a model from Galform plus dark matter only simulation. And what's interesting is that, when we first saw this, when we first plotted this didn't agree, and that's because the redshift of reionization in Galform is 10. So we basically had the population down here, and it wasn't working at all. The redshift of reionization is 6, we get very good agreement. And this actually agrees more with like CMB, higher redshift studies, at least for when reionization ends. And I think it seems like a bit of a fluke. What's even more fluky is that when we did this is before we got better constraint on the halo mass, the mass range that we used was 1 to 1.3, which again is exactly what the range that we think that we're in now, at least converge to. Again, this is where we get this really good agreement. So again, I think there's a lot more work to be done on this. We have a very simple model of reionization. But I think it just shows you that the shape of this, and especially when we find more ultra-faint dwarfs we can get a better handle on, can tell us something about the early universe. Okay, so the final thing related to this, so this is kind of using this near-field cosmology aspect and then going back to why galactic archaeology also matters for near-field cosmology, is a paper that, again, Saunak led, which came out a few months ago now, looking at how many ultra-faint dwarf galaxies we expect given the assembly history of the halo. Okay, so massive halo matters, redshift of reionization matters, and also the assembly history matters. So there's a lot of things that you need to worry about in order to get, if you want to probe cosmology, you have to worry about the other stuff as well. And this was particularly motivated because we think there were early massive accretion events, and also we know that the LMC was accreted relatively recently. And so what he found is that typically, if you have a Gaia sausage type event, you have a larger number of ultra-faint dwarfs today. Okay, that was he found. Actually, and it's more of an influence than the recent accretion of the LMC. So this is kind of, again, this means that if we really want to put all these things together, we'll be able to probe cosmology. We do need to understand what the assembly history of our galaxy is too. Okay, and I just wanted to put that up very briefly. Okay, so the final thing I want to say is mainly what the most of the work I've talked about has come like in the last couple of years. There's been a lot of progress, not just from my team, also from others in this field. But luckily for us, even though like Gaia's been such a massive influence, it doesn't end there. So of course, we still have more data releases to come, which I'm sure will come up with new things. But also we have the spectroscopic surveys complementing those. I'm sure a lot of you here know about these. For example, DESI, which has already started. Weave, which these are both going to survey the northern sky, and of course Foremost, which is for the southern sky, which is going to give this kind of 60 phase space out, probably out to around 50 kiloparsecs, if not further, over the whole sky if we can combine all of these things. And again, I say plus because it's not just phase space, also chemistry, which we're going to get from the spectroscopic surveys. So I think there's a lot more to come in this field, and a lot more data that we're going to have to play around with. And then looking even further ahead to what I like to say the era of LSST. So this is more like another 5 years probably, and some more to go. That we're going to move into this kind of era where we're going to have a very deep, wide image of the universe. For Milky Way studies, this is particularly exciting, of course, in terms of discovering new ultra-faint dwarf galaxies, which, as I mentioned, these are very important for cosmological probes. And then also just the idea that we can map, not the populations in the halo out to incredibly large distances because there's such a deep survey. And again, that's not for a while, but it just shows that the future in this field is incredibly bright. Now, as well as the observations, there's also the simulations that have to go with it. And I'm not personally a simulator, although I analyze simulations quite a lot. But I think it's fair to say that we're behind, on the simulations rather than the observations. I think the observations have greatly overtaken where we are at in the simulation. So the future directions, actually resolving the ISM in dwarf galaxies, actually modeling that better. There's efforts in Durham for Colibri and also here called EMP. Swift is a code that Durham's developing, which is, all I know about it is that it's better than everything else, and it's going to do everything faster. But I think everyone's very excited about that in Durham. Still, for the ultra-faint dwarf galaxy regime, we're still going to need these semi-analytical models that we use because these are incredibly low mass and be really difficult, even in the era of Colibri, to do this. So we're really going to need to think about, we use a very old model to do this, so we're really going to need to think about updating this. And of course, even though, personally, I think it's kind of premature to do the mock observations with simulations that we have today because there are a lot of problems with them. But it is somewhere we need to go, is looking at these simulations in the same way we look at the observations. There have been efforts toward this, Gaia, and also I know the Latte group have done a synthetic survey. And again, I think we'll be doing that more in the future. And I think the summary I want to give is that the reason I worked on this so much is that I think it has so much to tell us about dark matter, galactic archaeology, and also probing cosmological models. I think Gaia has completely changed the shape of the field. If I think about what it was like when I started my PhD, I think most of the work I did was on SDSS data. And now for the young people working on this, the kind of exquisite data they have to work with, I think is really exciting. And I think that kind of is going to continue into the 2030s with something like LSST coming up as well. I think if we really want to understand all these questions, we don't need to just mine these survey data. We need to also make use of the simulations and by a really concerted effort into understanding those a lot more. But I'd say just generally my conclusion is I think the future is incredibly bright for this field. Thanks.
Thank you so much, Alice, for a truly fascinating talk. I'm sure there are many questions and comments, points of discussion from the audience. I know I have many, and while the rest... Ralph, good.
Thanks, Alice, for this very nice overview of what we can learn about our own galaxy from all these beautiful data. So I was wondering what simulation you can recommend that takes all these constraints into account. I mean, we are looking at Caterpillar, we are looking at Auriga, Milky Way type of things, and they all fit the mass to some degree, they get the satellites to some degree, but these sausage orbits and all these other things that you talked about, they are not studied or included. or use to constrain. Is there some simulation approach that really tries to match all these additional constraints that you talked about? I think that would be extremely useful.
Yeah, I mean, there's different approaches how you use simulations. One is you want to find the exact Milky Way, and I think as we get more and more data, that becomes harder and harder, right? Because then you say, I want an LMC, I want a sausage, I want this, and I want that to happen. And I think probably if you're going to go down that route, you need the constrained realization type of thing.
Are people working on this?
I'm not sure definitely for the local group in terms of getting, but I think in terms of the specific assembly history, I think probably the answer would be, for example, for Auriga, which is like quite a large suite of relatively high-res simulations, there's 30, which is considered quite high at the resolutions you need to do this. That's not enough to do all those constraints. So I think really we're talking about and I said that Swift is this amazing thing, if something like that can be up and running, and we can really improve the codes that much, then that would be one way to do it, is just to get loads more. But I think the problem is the more constraints you have, the more simulations you need. So I think it depends on the question. For example, if you care about the outer parts of the halo, you probably don't need all the special hydrodynamics that need to go in to make the disk. Okay, so it depends on the question. You could put in a semi-analytical type description, but again, we don't know how to do that at the low mass scales. So it's a massive challenge how to approach it. And I think when you ask with a caterpillar whether that's the best way, or a hydro simulation, I guess I would say both. We have to do both. There's not a better way. It's just some are better for different questions. I mean, that's a very diplomatic response, right? I'm good at that, but yeah.
I'm specifically worried about the very low mass end, because we can put in. So I'm specifically worried about the very low mass end, because we can put in our population 3 and 2 star formation, and we can make predictions of the satellite population and the galactic archaeology, the extremely metal poor stars of the Milky Way. So I'm wondering whether there is something better than Caterpillar or Auriga on the market that makes better constraints on the actual dynamics.
I don't think at the moment, but I think there will be. I think that's, I think modeling the dwarf galaxies is where people are going. I think, to be honest, at the moment, I think the ultra-faint regime, we're probably better using the kind of semi-analytical models rather than we are building them in the hydro simulation. I think that's where they're going towards, but I think at the moment, at the scales that we're at and the subgrid methods they have, you're just as good doing some semi-analytical model on top of a dark matter simulation. Yeah.
The Enceladus sausage, what did it collide with and what happened to it? So it collided with the Milky Way. Do we see that?
So yeah, I don't know if you saw a recent paper that Vasily had out called The Splash. I mean, he's very good at coming up with catchy titles, as you know. So there's now, I think that the effect on the disk, for example. So there's a paper that Vasily did, basically finding what he calls splash material, which I think has been kicked up from that event, which has also been called in situ halo formation. Also, on a more theoretical side, it's not out yet, but Rob Grand is writing a paper about how an event like that affects the formation of the thick disk. Because maybe it is actually the trigger for the thick disk formation. That's currently been written using Auriga. Again, that's a theoretical paper though, but we should have predictions of what that should look like.
You showed on one of the last plots the fit to the observed number counts of very faint dwarf galaxies. I presume that the model for that was a CDM model. Is it possible to do that with a warm dark matter model, and if so, what changes do you have to make to your feedback recipe?
Yeah, that's an excellent question. So one thing I didn't talk about, so this is this. So yes, this is cold dark matter. The twist is why these dwarfs are so exciting is that yes, if we change the dark matter model, the number of ultrafaints goes down. Okay, so one thing that's going to hold this back. In some point, it's almost the effective reionization and your dark matter model could also be degenerate, right? Which is a problem. You could argue that if you had good enough data, you could tell these apart, but I think that coupled with the fact that these low mass end, I mean, we have a model for them, right? This is just one model, but how we model that low mass end, so this is using gal form. So the feedback and what mass halos these go in is still incredibly uncertain.
Yeah, that's right. So you think you could do it?
Yeah, I'm an optimist. I'm optimistic, but yeah, I think this is number counts. This is one way, okay? But I think in the number counts, and again, I mentioned how the assembly history changes the number as well. So there's a lot of things that are degenerate in this regime. This bit doesn't get affected by as many of these things, so we can pin this down better. But the numbers here, I haven't even seen the prediction for dark matter models, okay? So I think, unfortunately, like a lot of things, I think if you want to pin down the nature of dark matter, you've got to understand galaxy formation on these mass scales first. So.
Thank you. Regarding this plot particularly, I guess in the Gal form model, reionization happens instantaneously everywhere, right? And there are suggestions that in the local group, depending on where the halos were at redshift 6 around the Milky Way or further away, they would have been reionized at slightly different times. Do you know that would affect the quality of the fit or things like that?
I mean, yeah, again, I mentioned there's a very simple model of reionization. It just says it happens, right? And I think, obviously, that's not very realistic. In terms of doing that, you need proper radiative transfer, right? Which is, again, this is another complication into these modeling, and I think that's what has to be done. And as you say, on local group, environment. That doesn't mean it can't be done, but I think that's where this needs to go. And with all these things, there's a lot of complexities that have to go into that. But yes, I think it needs radiative transfer to get that properly.
I have a question about the definition of halo throughout this talk at some level, because of course you quoted the mass for the stellar halo at the end, and just curious if that basically includes an extrapolation down to the central regions, where maybe early on, when the Milky Way was still low mass, you ended up building sort of more like a bulge-like spheroid in the center. And then related to that, if you infer the mass of the Milky Way, the dark matter halo mass, you showed that this is quite strongly dependent on radial anisotropy. Like, you use that with one of the free parameters that you measure. But of course, the galactic halo has a wide range of radial anisotropies, and of course, if something like the sausage event dominates, then that is one bit that has a high radial anisotropy, but that must then also be stochastic and subject to Poisson statistics, because there's one accretion event that contributes to that. So how do you deal with those elements?
So the first question about total mass, the definition. In our mass definition, can't remember quite what Ted's was, but it's basically 5 kiloparsecs, so nothing less than 5. I mean, we do have a parallax cut, which basically loses the inner regions, and we say to 100. We assume the density profile is such that there's not going to be a lot of mass beyond that. But yes, it's making the assumption that we're not missing a lot in that 5 kiloparsec regime. In terms of the radial anisotropy, I guess you're talking about the escape velocity work.
Yep.
So one of the things, interesting things there is that we only care about the tail. Okay, so if you make the assumption that the sausage dominates the tail, then you can say that. It doesn't mean it has to dominate the low velocity end.
That's fair. Okay, so basically, because the prediction for the Kraken accretion event, based on where the globular clusters are sitting, is that it's mostly residing within 6 kiloparsecs. So then your mass budget problem, say, for the stellar halo is not affected by the fact that it would be 2 instead of 1 accretion event. So that would help a little bit.
Yeah, that's a good point.
Yeah.
Okay.
Any further questions? And I should also introduce or announce next week's joint colloquium, which is by Christine Wilson from McMaster, who's going to be talking about dense gas and star formation in nearby galaxies using ALMA. So I look forward to seeing all of you again next week. And for now, let's thank Alice again for a wonderful talk.